Hello student, good morning to everyone. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the Friedel-Crafts reaction. As we know that Friedel-Crafts reaction, it is divided into two types. One is called as a Friedel-Crafts alkylation reaction and another one is known as a Friedel-Crafts oscillation reaction. Friedel-Crafts alkylation reaction means what? Friedel-Crafts alkylation reaction is an electrophilic substitution reaction in which one or more hydrogen atom of the aromatic nucleus are substituted by alkyl group is known as Friedel-Crafts alkylation reaction, and that Friedel-Crafts alkylation reaction mechanism of that Friedel-Crafts alkylation reaction involves three steps. And the step also we know that first one is the formation of the generation of electrophile. Second one is the formation of the uranium ion or the sigma complex, and third one is the formation of the product, that is aromatization. And their limitation also we have seen why it has a limitation, means polymerization and the polyalkylation. These are the major or the serious drawback about that Friedel-Crafts alkylation reaction. Today what we are going to learn? Today we are going to learn about the second one, which is a Friedel-Crafts oscillation reaction. What do you mean by the Friedel-Crafts oscillation reaction? Similar to as a Friedel-Crafts alkylation reaction, where the alkyl group we are introduced into as a benzene ring and we are getting as a formation of the product. But in this case, Friedel-Crafts oscillation reaction means what? We are going to introduce this type of the acyl group in presence of the again AlX3, means Lewis acid is used here. Without Lewis acid there is no Friedel-Crafts reaction, and therefore Lewis acid is essential to carry out the reaction. Without the Lewis acid there is no Friedel-Crafts reaction occur, either Friedel-Crafts alkylation or Friedel-Crafts oscillation reaction. These two reactions do not occur without the Friedel-Crafts alkylation Lewis acid. What is the role played that Lewis acid in this particular aromatic electrophilic substitution reaction, or in particularly in a Friedel-Crafts reaction? The role played by that Lewis acid to generate the electrophile, and once that electrophile is generated, it can attack to the benzene nucleus, and then the formation of the product, formation of the intermediate, which is known as a uranium ion, or what we can call it as a formation of the sigma complex. And that sigma complex or whatever that uranium is formed, that is then last step is aromatization. The driving force behind that formation of the substitution product is aromatization, and we are getting back or the whatever original compound, aromatic compound, we are getting that one. So this is known as a Friedel-Crafts oscillation reaction. And the reason behind it, Friedel oscillation reaction, why it is an important one? Because it is important because we can introduce the whatever alkyl group we want, desired product we can prepare, and that's why Friedel-Crafts acylation reaction is superior than the Friedel-Crafts alkylation reaction, because in a Friedel-Crafts alkylation reaction we have seen there are the two serious drawbacks are there. Number one is polyalkylation and number two is polymerization. So to avoid such type of the polyalkylation or polymerization, he discovered the another method that is called as a Friedel-Crafts acylation. It is what we can call it as a superior than the Friedel-Crafts alkylation reaction, and the mechanism of that Friedel-Crafts acylation reaction also involves three steps. Number one, as usual we know that mechanism of that Friedel-Crafts alkylation reaction, step number first is this one, formation or generation of electrophile. Here is a generation of electrophile, and these electrophile is generate due to the presence of the due to the presence of Lewis acid. The Lewis acid which is used here in this case is a ALX. If you take as a general reaction over here, but let us see here general reaction. Suppose we have this one. Let me tell here, let me take here the suitable example, CH3 C double bond O Cl, acetyl chloride I am taking over here, and now it is treated with AlCl3. As we know that it is a Lewis acid, and Lewis acid, the function of Lewis acid to generate the electrophile, this we are getting here CH3 C double bond O, positive charge over there, and plus AlCl4 which is a minus, that is a conjugate base is formed over there, and this is nothing but as a electrophile, and this we can write this lone pair present over there, so you can write this way also, CH3 C triple bond CO. And now look at here, now is a 3 carbon with that oxygen atom, and therefore we can call it as we can put the positive charge on the oxygen atom. We can write either this way or this way. So this is the first step taking place in the Friedel-Crafts acylation. Acyl group means this group, you remember, this is the acyl group we are going to introduce. So this group over there, and therefore this is the first step which is a generation of the electrophile. Here the electrophile is generated over here. This is the electrophile, right, and this is the conjugate base. Now is the step number second, as usual similar to as a Friedel-Crafts alkylation. In that step we have seen that is a step number second is what is that, formation of uranium ion. That step number second is a formation of uranium ion. Formation of uranium ion, or what we can call it as here, formation of the sigma complex. So this is the step taking place in the Friedel-Crafts acylation reaction, similar to as a Friedel-Crafts alkylation reaction. And as we know that the starting material we have taken here is a benzene that will be treated with the electrophile is going to attack over there, C double bond O, positive charge over there. Now as we know that, for sake of convenience, I am writing that hydrogen atom like this, one of the hydrogen atoms, so that you can see that reaction, and this step is a very slow step, and as we know that slow step is a rate determining step, RDS, rate determining step. What is happening, this double bond is now attacking on that carbocation, that the carbonyl carbon atom here is a electron deficient in nature, and therefore the bond is formed between this benzene carbon atom and this carbonyl carbon atom, so that you are going to get here the product, the double bond which is as it is, this another double bond I am writing as it is. Now this hydrogen atom I am showing like this, and this there is a attached this acetyl group C double bond O CH3. Now when this double bond moves likewise the positive charge should be present at this corner point, and now this is called as a uranium ion. Uranium ion, and this uranium ion also we know that it is what we can call it as a formation of the sigma complex, right? And now we can represent this uranium ion in this manner also, similar which we already seen in a previous example. Positive charge you can put as it is. Here is a hydrogen atom, and here you can write C double bond O and the CH3. So this is the what we can call it as a sigma complex formation taking place. And as we know that the last step means third step in a Friedel-Crafts oscillation reaction, and what is that third step? Always there is, we know that the aromatization. Now if you look at, if you observe these two structure carefully, our uranium ion is nothing but as a aromatic carbocation over there. This is a aromatic carbocation, and that aromatic carbocation is a non-aromatic in nature, and there but it get stabilized due to the resonance effect. This shifting over there, positive charge again shifting. Likewise that carbocation, benzene carbocation or the uranium ion well stabilized due to the resonance structure, and therefore it is a even though it is a difficult step, but it is a very essential step, or the what we can call it as a prominent step present in that Friedel-Crafts oscillation reaction. And the third step number 3, as we know that it is a aromatization, or what we can call it as a abstraction of proton, you can call it. And what is happening here in the aromatization, the driving force behind it for the formation of substitution product is that aromatization, and therefore we are going to get over here. Here you can write this uranium ion as it is over here. Here a hydrogen atom, C double bond O, CH3, this group as it is, and then this step is a very fast step. And in first step what is going to happen? Al Cl4 minus, this is a Lewis base or the basic anion which will abstract this proton. Here is a positive charge. Now this aromatization is retained over here. Even it is a non-aromatic compound, this one non-aromatic compound now become as a aromatic substituted product over there. This double bond I am putting as it is, this double bond also as it is, then C double bond O, and then CH3. So this is, and the side product, don't think about side product, but let me write over here. Here is a AlCl3, whatever original catalyst you are using, it is involved in the reaction, but at the end of the formation of the product it is regenerated, and there is a fumes of HCl goes in the atmosphere. So in this way, and the name of this compound, as we know that it is a acetophenone, right? This is acetophenone we can prepare very easily by using as a this type of the compound. And why? So this is all about the mechanism of that Friedel-Crafts alkylation reaction, right? And now why this Friedel-Crafts oscillation reaction, what is the reason or what is the purpose behind it? Why Friedel-Crafts invented or discovered, and which name is given as a Friedel-Crafts oscillation? Because previously at the early days he had prepared the Friedel-Crafts alkylation reaction, but he found that there are some serious drawbacks are there. We cannot prepare such type of the toluene in the laboratory by following that rule. A number of mixtures are getting, and that's why he thought and he discovered the another method, and that's why it is known as a Friedel-Crafts oscillation reaction. It is a superior, it is a better than the Friedel-Crafts oscillation reaction. Why? The reason behind it, let us see here why it is superior or better than the Friedel-Crafts oscillation reaction. Let us see here over. Now what is going to happen here when he prepared that, suppose we want to prepare this type of the compound from benzene, you want to prepare this type of the compound, right? This is the compound, you are going to CH2 and the CH3. This is a propyl benzene we want to prepare here, but this propyl benzene, how do you prepare this? This we cannot prepare by following as a Friedel-Crafts oscillation reaction. If you follow that reaction, if you use as the starting material that one, you will end up with the cumene, formation of the cumene, which is a major, and that propyl benzene we are getting very little in amount, means very small in amount, and for that purpose we want to prepare as a propyl benzene. We can start with the starting compound is the benzene like this. So as we know that this is the structure of benzene, if you treat with this CH3 CH2, then C double bond OCl in presence of AlCl3, what you are going to get over here? First one you are going to get here, because we want to prepare the target molecule like this one. We are going to prepare the compound, this one CH2 and CH3, right? This is a propyl benzene we are going to prepare, but let us see first one is this one, and when heated it gives the product this one, because here the possibility only C double bond O CH2 and CH3, this type of the compound we are going to get in this case. This is known as a Friedel-Crafts oscillation reaction, and here we introduce as a this group, and further we want to prepare as a this one. So you can convert that carbonyl group in T.Y.B.Sc. You already learned that the conversion of carbonyl group into as a hydrocarbon. What are those? Do you remember that? The reduction of that carbonyl group. If you use as a Clemmensen reduction in an acidic medium, the carbonyl group is converted into as a that hydrocarbon CH2 group. Clemmensen reduction, as we know that. Clemmensen reduction. And what is that reagent used in the Clemmensen reduction? I think H2 in presence of zinc amalgam, ZnHg, zinc amalgam in presence of HCl, that H2 in presence of. This is the reagent used, zinc amalgam in presence of HCl, that is the reagent used in a Clemmensen reduction. What it will do? This is used in an acidic medium. If used as an acidic medium, you will get as a this carbonyl group is converted into as a this one. So in this way, or you can use as a Wolff-Kishner reduction also. Wolff-Kishner reduction also used for the conversion of this. Wolff-Kishner reduction, the reagent I think used there, hydrogen hydrate in presence of H2N NH2 in presence of OH minus. So that is the reagent is known as a Wolff-Kishner also, but it is in a basic medium we can get as a this one. And again in a neutral media, so we can use as a what that sulfur and the Rane nickel. So you will get as a that type of the compound in a neutral media. So we will get as a this one. Suppose again if you want to prepare this type of the compound is there. Suppose you have another one, CH3, CH2, CH2, then CH2, CH2, C double bond O, Cl in presence of AlCl3. What do you get? You are going to get here. So let me write here. So you are going to get here Ca. So here mainly as a this type of the compound you are going to get this one. C double bond O, then CH2. How many CH2 are there? 1, 2, 3, 4. So I am writing in short 4 and the CH3. And now if you treat with that Clemmensen reduction, what do you get? You are going to get as a this type of the N hexyl group, means 4, 5 and 6. So here you are going to get as a CH2, 5 and the CH3 group. This type of the compound you can prepare by using selectively, and that's why it is a superior reaction over that Friedel-Crafts alkylation reaction. And now what are the other reagent used to introduce that acetyl group into that? So let us see, suppose there are such type of the compounds are there. Suppose you have a starting compound, this one, benzene, that will be treated with CH3, C double bond O, OH in presence of H plus sulfuric acid, or you may get here also as a acetyl group you can introduce here, C double bond O, CH3, acetophenone you can get over here, right? And so this is what we can call it as a very good method for the preparation of acetophenone. Or you have a starting compound again as a benzene, that will be treated with acetic anhydride, CH3, C double bond O, then C double bond O, CH3 in presence of H plus acidic medium, you can introduce the C double bond O and CH3 group, acetophenone. So in this, by using as a different starting material and the reagent, I think here you can use as a H plus, or you can use as a Cl3, Lewis acid, so that you will get as a that type of the compound over there. So these are the some of the what we can call it as a reaction which shows the Friedel-Crafts acylation reaction. So in this way we have seen there are the different reagent we can use there, and we will get the formation of the acetophenone, or we can easily introduce that acetyl group into as a benzene, or we can introduce the longest chain, but one step is increased, that is by using as a Clemmensen reduction or by using as a Wolff-Kishner reduction. You can convert that carbonyl group into as a hydrocarbon, which you already learned at your T.Y.B.Sc level. So this is all about the what we can call it as a Friedel-Crafts alkylation reaction. But even though these are the reactions are there, now that Friedel-Crafts alkylation reaction also has some limitations. What are those limitations here? The number one limitation, whatever the product is formed, suppose this one, and this is a less reactive as compared to as a benzene, because there is a carbonyl group, it is electron withdrawing group, and therefore the reactivity of that benzene moiety is decreased. So there is a lot of difficulty in introducing the another group into as a benzene ring. So that is the one of the what we can call it as a limitation of that Friedel-Crafts alkylation reaction. And similar to Friedel-Crafts alkylation reaction, Friedel-Crafts acylation does not take place with phenol and the aromatic amines. Remember the whatever limitation in case of what we can call it as a Friedel-Crafts alkylation reaction, the limitations of this also. And what is happening, this Friedel-Crafts acylation reaction do not get with that. Suppose you have this one, OH, phenol, or the amine like as a aniline, let us see, NH2 amines are there. If you treat this compound with what we can call it as like this CH plus C double bond O, then Cl in presence of AlCl3, there will be no reaction. Similarly here also CH3, C double bond O, Cl in presence of AlCl Cl3, there will be a no reaction. Why there is a no reaction, or what is this is a major limitation of that Friedel-Crafts oscillation reaction is that phenoxide OH group is a more reactive, it get coordinated with AlCl3, and we are going to get this type of the compound. There is O, then H, and then AlCl3, here the positive charge over there, and so that type of the salt get formed, and therefore this becomes as a deactivated, and no further they get coordinated with that hydroxy group or here with that amine group, and therefore they do not produce the AlCl3. They get here is a positive charge, here maybe as a negative charge, and therefore this is another major problem of the major limitation of that Friedel-Crafts oscillation reaction. So I think with this we have seen as a limitation of the Friedel-Crafts alkylation reaction. And suppose you then planning the synthesis of diaryl ketone, suppose you have this planning the synthesis of diaryl ketone. Let us see another one of the example here, planning the synthesis of, now this planning the synthesis of diaryl ketone, planning the synthesis of diaryl ketones. Now suppose you have a starting material is this one, right? And now you have this one, this is a starting compound, here O2N, and here you can take as a C double bond O CS3, right? Not CS3, here you can take as a H, that is a here is a benzyl chloride, and then take another compound, here is a benzene, and if it is treated with AlCl3, what is going to happen? And if you take as this compound, here is a O2N nitrobenzene, and that will be treated with this one. Here what is going to happen? C double bond O Cl in presence of AlCl3. What is going to happen over there? Suppose if you take as this type of the combinations are there. If you look at, this is a meta-nitroacetyl benzyl acetyl, and that is treated with benzene, and here is a nitrobenzene with that benzoyl chloride. This is known as a benzoyl chloride. And now what is happening? The nitro group present on the benzene ring, it get deactivated. As this one, we know that this is a benzoyl chloride, that positive charge, but it is a deactivated, so there will be a no reaction here. No reaction will take place, and suppose here you may get as this type of the compound over there, here O2N, and then C double bond O, this type of the compound you will get there. In a first case, there will be a reaction. So while planning this synthesis of aryl ketone, you should remember that if electron withdrawing groups are present in a aromatic compound, this type of the aromatic compound do not undergoes the Friedel-Crafts alkylation reaction. But if there is such type of the combinations are there, electron withdrawing group present that benzyl chloride must have then benzene, they can produce, they can give the this type of the aromatic ketone, remember. So I think with this we have seen the Friedel-Crafts alkylation reaction with their mechanism, different how it is superior than the Friedel-Crafts alkylation reaction, as well as even though it has some superiority than that alkyl Friedel-Crafts alkylation reaction, but it also has two limitations are there. While the synthesis of and how this Friedel-Crafts alkylation reaction do not react with that phenol and the amines, that also we have seen. And while synthesizing as a aryl compound, aryl ketones, how we can plan that synthesis, that is also as a important one that we have seen. I think with this we have completed this Friedel-Crafts reaction completely over here. In the next time we are going to learn that is a diazo coupling reaction. Let us stop today here. Thank you. Have a nice day.